So let's look at how to name one. First thing we need to do is identify the longest chain, and the longest chain may not necessarily be straight. So if we take a look at this particular carbon, if we go this chain here, we have 1, 2, 3, 4 carbons this way with 2 hanging off the end. But if we look at it this way, we have 1, 2, 3, 4, 5 carbons. So the green line represents the longest chain, even though it's bent. And so if you want to straighten it out to make it easier to identify, it will look like this. When we're drawing organic molecules, the hydrogens tend to be ignored. They're understood. We put functional groups present because we need to know them to know the name. And we put in multiple bonds, but we tend to ignore hydrogens just because it takes so long to write them. So when I write the chain like this, I have 5 carbons, so that's a pent. If I look at the molecule, I see it's all single bonds, so it's going to be pentane. On the pentane long chain, I have this carbon right here, and this is actually a CH3, and it is a functional group. So I have to figure out how to name that. So for naming hydrocarbon functional groups, I'm going to take however many carbons are in it, use that as a stem, and then add the suffix YL. So CH3, when it's a functional group, is going to be a methyl. I'm given an empirical formula, C6H14, several ways that I can organize these 6 carbons and 14 hydrogens. I can write them as a long chain, where I have just plain old hexane like this. I can write them as a chain of 5 with a functional group here. I can take that same 5-carbon functional group and I can move that methyl group to a different carbon. There are actually a lot more other possibilities. We're just going to start with these 3 and talk about how we name them. So hexane, just a straight chain 6-carbon, is easy. Both of these that have 5 chains are going to be pentane, and they have a methyl group attached, but in different positions. They're not the same exact pentane because that methyl group is on a different carbon. So we have to figure out how to differentiate them when we're naming them. The way we do that is we start counting carbons in the main chain, and we want to put the most important functional group on the lowest number carbon. So I can number these from left to right. So I have carbon 1, 2, 3, 4, 5. Or I can start from the other end. It doesn't matter which end I start from. The goal is I want to start from the end that will give my most important functional group the lowest number carbon. So for my left-hand pentane structure, it doesn't matter because the methane in both cases is on carbon number 3. In the right-hand case, it does matter which way I start from because if I start counting from the left, my methyl group is on the 2nd carbon. If I start counting from the right, my methyl group is on the 4th carbon. So in this case, I would want to start from the left because that gives me a lower number for methyl. So when I name this, I'm going to put the number first to identify where the functional group is, and then the functional group. So this one's going to be 3-methyl, and then the main chain, pentane. This right-hand one, the carbon is on a different group, so this is going to be 2-methyl pentane. Standard writing tend to put a hyphen between the number and the functional group, and then a space between the prefix and the main chain. Sometimes they run together. It's not critical. When you're putting numbers on and identifying positions for your functional groups, again, you want to have the most important functional group has the smallest number. So how do I know what functional groups are and how they're important compared to each other? Well, here's a list of the ones that we're going to be dealing with from least to most important. So least important are the multiple bonds. Next are hydrocarbon functional groups. Then come halogens. Then come oxy or oxygen-related groups, and the most important ones are the nitrogen-based groups. And we'll have a chart momentarily that walks us through the oxy groups and nitrogen-based groups. Okay, when I'm naming alicyclics, I have a ring structure, and so 1 could be anywhere. 1 being the smallest number. Remember, I want the most important functional group to get the lowest number. So I can go clockwise around this ring, I can go counterclockwise around this ring. I've got 2 functional groups. I have a double bond here, and I have a chlorine here. So I want to count around the ring to ensure that both of those 2 functional groups get as small a number as possible. From the previous number, we found that halogen is more important than double bond. So I want my chlorine to be number 1. So I'm going to start my counting there. And from there, I can either go clockwise or counterclockwise around. If I go clockwise, then I'll hit the double bond with carbon 2. So I'm going to go clockwise around the circle. So the way that I would name this thing is, first of all, I'm going to identify the functional group. So I have a chloro group and I have an ene ending. My chloro group is on carbon 1 and my double bond is on carbon 2. And I have a 6 carbon ring. So I've got a cyclohexene and the ene is on carbon 2. So I'm going to do 2 cyclohexene and I'm going to do 1 chloro. So 1 chloro, 2 cyclohexene. That means the chlorine is on carbon 1 in the ring. The second carbon in the ring is where the double bond starts. And when you name double bonds, you always name the lower of the 2 carbons as the identifier. Structural isomers are compounds that have the same empirical formula, but they have different structures. We saw structural isomers earlier when we saw 3-methylpentane and 2-methylpentane. So those 3 compounds are all very different, but they are considered structural isomers because they all have the same empirical formula. Geometric isomers are a little bit more interesting. Geometric isomers are sometimes referred to as cis-trans isomers, and they require double bonds. The reason that they require double bonds is you can have rotation around a single bond. You do not have rotation around multiple bonds. The fact that there's no rotation means that I can have things positioned opposite to each other and they are different. I'll show you what I mean in a minute. If we look at a compound that has 2 carbons, double bond, we have hydrogens on it, and we'll put 2 chlorine functional groups on it, and we'll draw this same compound a little bit differently. There's another way we could draw this, but we'll save that for later. Okay, so I have 2 carbons, so that's eth, double bond, so it's ethene. I have 2 chlorines. 1 chlorine's on carbon 1, 1 chlorine's on carbon 2. So it's going to be 1,2-dichloro. So far the name is the same for both compounds, 1,2-dichloroethene. How do I distinguish between the 2 of them? Because these are geometric isomers. The chlorines are on the same side relative to each other on the left-hand one, and they are opposite or across from each other on this one. So we're going to use 2 Greek terms again. We're going to use cis, meaning the same side, and we're going to use trans, meaning opposite sides. So for the compound on the left, it's going to be 1,2-dichloro. So for the compound on the left, it's going to be cis 1,2-dichloroethene. For the compound on the right, it's going to be trans 1,2-dichloroethene. So when we're dealing with geometric isomers, they're the same structural formula, they're the same empirical formula, but they are different geometric isomers because of the positioning of those functional groups. Okay, we said before that aromatic compounds are based on benzene, so there's the benzene. Remember, all the bonds are equal length. Even though I show the left-hand diagram with 3 double bonds and 3 single bonds, remember there's resonance, so that allows all the bonds to be equal in length. We have pi bonds, so the electrons are delocalized. And when I stick functional groups on benzene, I name it similarly, although there's some common benzene compounds with the single functional groups that actually have different names, more common familiar names. So I have a methyl group here, so that's going to be methyl. Since there's only 1 functional group, the number 1 carbon is implied, so if you want to, you can put it in, but you don't have to when there's only the 1 functional group on a ring structure. So this will be methylbenzene. Methylbenzene also has a name among organic chemists. It's called toluene. This is an OH group. It is not a base. It is an alcohol functional group, and we'll get to oxy functional groups shortly. So the name that you would use is benzene, and then if we're naming it based on an alcohol, it would be benzenol. I've never seen it called that. The more common name in the essentially now standard name is phenol. So when you see benzene ring with an OH stuck onto it, phenol. The thing is that this phenol can also act as a functional group on other. Benzene itself can act as a functional group where it's attached to a long chain carbon. So I would have the benzene ring, and rather than hydrogen on that carbon, that would be the attachment site to the main chain. And when it acts as a functional group, it's called a phenyl. 1 carbon, remember, is methyl, 2 ethyl. When I have a benzene ring acting as a functional group, I've got that YL ending, it's called a phenyl functional group.